Hi all, in this video we will be looking at what is sorting, what is bubble sort, and the mechanism of bubble sort, the implementation of bubble sort in Java, and we'll also be looking at the time complexity and what kind of optimizations we can make to bubble sort algorithm. So let's start with what is sorting. As you're already aware, sorting is arranging a set of elements in some specific order. For example, if the elements are numbers 1, 2, 3, 4, 5, this is an ascending order. And if we have something like 10, 5, 3, 2, minus 10, this is a descending order. Now, it's important to understand that the elements need not always be numbers. For example, let's say that you have a set of books, and the book that you use most often will be at the top of the pile, and the book that you use least often will be at the bottom of the pile. Therefore, you're actually sorting your books in the order in which in the order of the frequency of usage of the books. So the book that you use most often is at the top, and the book that you use least often is at the bottom. And the rest can follow the similar order. So sorting is not just restricted to numbers, it can be used on all kinds of objects. Now let's have a look at what is bubble sort. Bubble sort is a sorting algorithm that is based on comparison. And what does it actually mean? Where does the name bubble sort come from? So the name bubble sort comes from the behavior of bubbles. If you've observed how bubbles behave, the larger bubbles tend to rise up faster than the smaller bubbles. Now, if you look into the physics of it, you can say that the volume of the larger bubble is greater and therefore it experiences a greater force, and so it rises faster than the smaller bubbles. But we are not really interested in the physics of it. We only need to understand the behavior of it. And the most important point is that large bubbles rise up faster than smaller bubbles. Now, in a very similar way, the bubble sort algorithm, which is appropriately named, the effects of the algorithm are very similar to the behavior of bubbles. Now let's just look at an example to understand why that is so. I'm going to show you the implementation of bubble sort in Java. So here we have the bubble sort algorithm. Let me just comment some statements. Now I'm running the code. So our input array is 100, 90, 80, 70, 60, and 50. Now this is sorted in descending order. Now what we're trying to do here is to sort the array in ascending order. For that, we have written a function called bubble sort. Now don't worry about the inner workings of the function. We're only interested in the black box view. So what this function does, it sorts the array, and after it sorts the array, we're going to print out the array and see the output. So now that I have run the program, it shows in the output the sorted array, which is 50, 60, 70, 80, 90, and 100. So obviously the algorithm is working. But let's look at how the algorithm behaves in the intermediate steps, or when the sorting is actually happening. So for that, I have commented out the final output statement, and I'm printing the array in the intermediate stages of the sorting, or the sorting algorithm. So now when I run this, if you can see here, in the first iteration or the first pass, the largest element has moved to the rightmost extreme. It was actually in the first position and it has moved to the last position. And in the second pass, the second largest element has moved to the second last position, which is 90. So what actually is happening here is that the largest element is getting sorted first, and in the second pass, the second largest element as well is being sorted, and in the third pass or the third iteration, the first three elements or the top three largest elements are getting sorted, and in the fourth pass the top four largest elements, and in the fifth pass the top five elements, and so in the sixth pass it should obviously happen that the top six elements will be sorted. However, we don't actually need the sixth pass. We only need 5 passes. And the reason for that is obvious. Once you've sorted the top 5 elements, the sixth element is automatically sorted. Therefore, if you have n elements, we only need n-1 passes or iterations. That's an important point to keep note of. Now let's look at what actually is happening in each of these passes or iterations. Let's look at the inner working of the bubble sort algorithm. For that, let's take a look at an example from Geeks for Geeks, which is a simple example. So we have this array 5, 1, 4, 2 and 8. In the first step, we compare the elements in the first and the second position, which is 5 and 1. Now, if the element in the first position is larger than the element in the second position, then we swap the two elements. So it becomes 1 and 5. Now, in the second step, we compare the elements in the second position and the element in the third position, which is 5 and 4. Obviously, this array is coming from this step. Okay, so we compare 5 and 4, and obviously the first element is larger than the second element, and therefore we swap it. So it becomes 4 and 5. So what we are essentially doing here is we are taking the larger of the two elements and we are pushing it to the right. That's what's happening in the first step. In the second step, we're taking the larger of the three elements and we're putting it in the third position, which is here. In the third step, we compare again the third position and the fourth position. And obviously 5 is larger than 2 and therefore we swap it. So in the third step, we take the first 4 positions and we take the largest number of all the 4 numbers and we put it in the fourth position. In the fourth step, we take all the 5 numbers and we put the largest number in the fifth position. Obviously here there's an important point to keep note of, that when we are comparing 5 and 8, 5 is smaller than 8 and therefore there is absolutely no need of swapping these two elements. The largest element remains in the correct position. So what we have done in the first pass is that the largest element has been sorted, or in other words, the last position of the array has been sorted. So when you look at the behavior of bubbles, obviously the larger bubbles rises up faster. In a very similar analogy, the largest element is sorted first. It's sorted first before any other element. Now, let's look at the second pass. In the second pass, our goal is to sort the second largest element. Obviously, we don't need to worry about the last element. Therefore, we'll be looking at the first pair, 1, 4. And obviously 1 is smaller than 4, so there's no need of swapping here. So next we'll look at the second pair, 4, 2. And 4 is larger than 2, therefore we need to swap it. And in the third step, we compare 4 and 5. And 4 is smaller than 5, therefore there's no need to swap it. Now, in the next step, we have 5 and 8. Now obviously 5 is smaller than 8, but it's also important to note that 8 is the largest element and it has already been sorted. So there's absolutely no way that you're going to change the position of 8, and therefore this comparison itself, this whole step itself, is redundant. It's not at all useful. So in the second pass, we only need 3 pairs of comparisons, or 3 comparisons. In the first pass we needed 4. In the second pass we only need 3. And therefore, following the same logic, in the third pass we only need 2. I hope you're following here. So now let's take a look at the example once again. I'm going to print the output. So in the first pass, 100 is compared with 90, then they are swapped, and then 100 is compared with 80, and then they are swapped, and then 100 is compared with 70, and they are swapped. 100 is compared with 50, and then they are swapped. 100 is in the last position and it's already sorted. Now we only need to worry about these elements. We only need to sort these elements. Therefore, with each iteration or with each pass, the number of comparisons will decrease by 1, or it will reduce by 1. Now, let's look at the working of the algorithm. So as I've said before, if the array is of size n, or if it has n elements, we only need n-1 passes or n-1 iterations. So we're going to have a loop, a for loop in this case, which runs n-1 times. If you look at the condition, I starts from 0 and I is less than array.length minus 1, or in other words you can even call it is equal to array.length minus 2. It starts from 0 and it goes till n-2. It's the same condition as saying that it is less than n-1. So therefore the first loop runs for n-1 times. Now, as we have seen previously, we need to compare the adjacent elements, starting with the first and the second element, followed by the second and the third element, and so on, till we compare the second last element and the last element. To do that, we have another loop, and in this case the loop variable is j. And as we have seen previously, for this example, we have 5 elements and we have 4 comparisons. Therefore, if we have n elements, the loop runs n-1 times. So if we have 5 elements, it should run 5 minus 1 times. Now, what about the second iteration? Once the first iteration is done, we can essentially discard the last element. We only have essentially the 4 elements. Therefore, the loop must run only 3 times. And what about the third iteration? We have only 3 elements. Therefore, the loop must run only 2 times. So to account for that, we are going to subtract the value I from the length of the array. So in this case, for the first iteration, the value of I is 0. So in that case, we will have j less than length minus 1, right? Now what happens when I is 1? When I is 1, we will have j less than length minus 2 because we have added minus I here. So when I is 2, we'll have length minus 3. Therefore, it's always going to run one time lesser than the previous time. Okay, I hope it's clear for now, as of now. So now we need to compare the adjacent elements. How do you compare adjacent elements? So you need to compare the jth position, the j plus 1th position, and if the element in the jth position is larger than the element in the j plus 1th position, then you swap, right? Very similar to the logic, exactly the same as the logic that we have seen here. Assume this is the j and this is j plus 1. If the element in j is larger than the element in j plus 1, then we're going to swap it. If the element in j is smaller or equal to the element in j plus 1, then we are not going to swap. We are not going to do anything because they are already in the correct order. So here, let's look at the code of swapping. How do you swap two elements? Well, you take a third variable and you call it temp or some random name, and inside that variable you will store one of the two variables, one of the two values that you want to swap. So I'm putting array of j in the temp variable. Now I can assign array of j to the same value that is present in array of j plus 1. So now both the values are equal. And next I can assign the value temp to the value array of j plus 1. Therefore the two values are interchanged in the array. I hope it's clear. So once we have done the swapping, it's done, it's sorted, it's completely sorted. Let's go through the example once again. Now I'm going to run the array again. So we have, so when I is equal to 0, we're going to sort the element 100. When I is equal to 1, we're going to sort the element 90. When I is equal to 2, we're going to sort the element 80, and so on and so on. And by the end of the loop, we will have sorted the entire array. By the end of the outer loop, not the inner loop. The inner loop executes every time for each of the outer loop iterations. I hope it's clear. Now, let's go back. So we have seen the mechanism of bubble sort. We have also seen the implementation of bubble sort in Java. Now let's look at the time complexity. So what is time complexity? Time complexity is a mathematical way of analyzing algorithms. So let's say I have a program and I call it my program.java. I'm going to run this program in two different computers. Now in the first computer, it takes 1.3 seconds. In the second computer, let's say it takes only 0.5 seconds. Now obviously the running time has changed between the two computers, but it's the same program. So does it mean that the time complexity is different in the both cases? No, it's not. Time complexity does not mean running time. Running time can depend on a lot of factors, the most important of which is hardware. Hardware as well as the software. So running time depends on the device. Therefore, running time is not really a good method of analyzing the complexity of an algorithm. What we really need to know is how many steps are involved in executing the algorithm. This is called time complexity. Okay, so now let's take a look at the implementation once again, and we'll try to analyze the time complexity of the bubble sort algorithm. So here, the most basic step that we are looking at is the comparison itself. I mean, the entire sorting algorithm is based on this block of code, nothing else. We are simply repeating this code multiple times, iterating it repeatedly. So how many times are we executing this code? That's all we need to know. So the outer loop executes n-1 times, okay, and the inner loop executes n-1 times for the first time, and for the second time it executes n-2 times, and for the third time it executes n-3 times. Therefore, if you sum it all up, the second loop n-1 times executes n-1 times when I is 0, when I is 1 it executes n-2 times, when I is 2 executes n-3 times, and so on. And what happens? When does it end? It ends with the last comparison, which is between the first and the second element, and therefore there is only one comparison in the end. So it ends with one comparison. So the second loop executes these many times. Now it's important to note that this block of code is executed just as many times as the second loop is executed. Therefore, for all purposes, this is simply a black box which runs in constant time. This block of code runs in constant time. Whatever that may be. It could be 0.1 seconds, 0.2 seconds, but it's a constant for a given environment, for a given device, for a given hardware, for a given software. This is constant. Therefore, it doesn't depend on the input. It only depends on the number of times the second loop is executed. And we've already seen how many times the second loop is executed. So the second loop is executed these many times. And what is the sum of this series? It's an arithmetic progression. If you remember the formula, the sum is equal to n over 2 times a plus l, which is the first element and the last element, and n is the total number of elements. So in this case, the total number of elements is n minus 1, because the series goes from 1 to n minus 1. So the total number of elements is n minus 1. So it's n minus 1 over 2 multiplied by the sum of the first element and the last element, which is n minus 1 plus 1, which is n. So the number of steps involved in bubble sort is n times n minus 1 over 2. We can actually expand this and say it is n square minus n over 2, or we can say that this is n square over 2 minus n over 2. Now we are only interested in time complexity when n is large or when we have large inputs, because for small inputs there is no point in analyzing the time complexity. Because in the industry we will always be dealing with large inputs. For example, let's say we have Facebook and you want to sort the users based on the location. In each location we may have hundreds of thousands of users, so it's simply pointless to analyze the algorithm for small inputs. So this whole mathematical field is developed assuming that the inputs are large. So when input is large, it means that n is large. When n is large, the most dominant term in this expression is n square over 2. The n over 2 will diminish slowly and the n square over 2 will dominate the value of this expression. Therefore, we can say that this expression is not linear, it is exponential. So the time complexity of this algorithm grows exponentially with the input, not linearly. Let's take a look at the graphs of time complexity. So here we have an example. When the input size is smaller, the number of steps is significantly lower than compared to the linear time. But we are not really concerned about smaller input sizes. We are only concerned about larger input sizes. So when the input size is large, for example, look at when input is 100. When it's an array of length 100, we have 10,000 steps. But if it is linearly growing, we have only 100 steps. And if it is logarithmically growing, by the time we reach 100 steps, we have not even reached by the time we have reached the input length 100, we have not even reached 5 steps. So that is the difference. When the inputs are really large, you will see the significance in the dominant term of the expression. So in this case, the dominant term is n square over 2, and therefore we can say that this falls under the class quadratic time, and we use this big O notation to represent the quadratic time class, and we say this whole expression is big O of n square. Okay. Now there's a small catch in the algorithm, which is the algorithm behaves the same way for all cases. So as of now, the worst case takes O of n square time. The best case takes again the O of n square time, and even the average case takes O of n square time. Or we can use a different notation here. We can say this is omega of n square, and we can say that this is theta of n square. Now, what can we do to improve the performance of this algorithm? If we go back to this example, now after the second pass, we have one more pass, 1, 2, 4, 5, 8. In the third pass, the array is obviously sorted, 1, 2, 4, 5, 8, 1, 2, 4, 5, 8. But still, we are comparing the two elements. We ended up comparing the two elements. Although we did not swap it, we still ended up comparing the elements, which is simply a waste of time. So what we can do is, if there is a whole iteration without any swaps, it means that the array is sorted. It means that the array is already sorted. Therefore, we need to count the number of swaps in each iteration. Okay. So we have a variable int swaps, which is initialized to 0 for every iteration, and for every swap. Once we swap it, increment swap variable. So we can say swap plus plus, swaps plus plus. Now, once the inner loop executes, if there are no swaps that have occurred, if swaps is 0, then we can simply break the outer loop. It means that the array is already sorted, right? So we have reduced the time complexity of the algorithm in the best case, which is if the array is already sorted, then we won't have to compare all the elements n square in these many times, n square minus n over 2 times. What we can simply do is compare all the pairs once, and if there are no swaps, it means that the array is already sorted, and the algorithm stops execution. Therefore, we are only comparing n-1 pairs for the n elements. Therefore, the best case would be omega of n. Okay, good. So we have covered everything, almost everything that I have intended to cover. If you still have any questions, please leave some comments. I will try to explain it. Thank you for watching.